So we've talked about whenever the elements are arranged on the periodic table that we see the periodic law apply. And that leads to some trends that will show up on the periodic table, and we're going to be looking at those. And the trends are seen as a gradual or increase or decrease in some value that we're looking at. And the trending is developed mainly on two properties of the atoms. When you take if you take AP chemistry or college chemistry, they probably go into a little more detail about that, but we're just going to kind of look at the big two things that cause a trend. So number one, when we talk about things on number one, it's going to affect trends within a group. And number two is going to affect trends within a period. So as you go down a group, each time you come down one period, you're adding another energy level. So each period adds another energy level to the nucleus. As energy levels are added to the nucleus, then you see an increase in shielding. And shielding is caused by the core electrons. So the valence electrons, the very outside electrons, those kind of become the most important ones. Those are either lost or gained whenever bonds are formed or shared. And the only thing that is holding a valence electron that's not just causing it to fly off in space is the positive pull of the nucleus. So you have your nucleus that's positive, your electrons that are negative. So they're being pulled toward the nucleus by that opposite charge. If I increase the shielding, so what that does, that increases different energy levels, and they're going to have electrons, and it kind of blocks that pull some. And then it's easier for that valence electron to be lost. So it's a sheer distance thing. We're going to look at something called Coulomb's law here in a minute. And in the formula, you'll see in the denominator, it has a radius. So if I increase that distance, the force felt by those valence electrons from the nucleus is going to decrease. So that's going to be the cause of some of the trends that we see. Now, if I stay in a period, then I'm on the same energy level. So it's not a distance thing anymore. But as I go across the period and I'm in the same energy level, I'm adding protons as I move down a period. So now I'm having more positive in the nucleus so it can hold the valence electrons more. And that's called effective nuclear charge, or sometimes you'll see it written as ZF. Z and then EFF as a subscript. So it's the effect of added protons to the nucleus as you move within a same period. And because I'm having now more positive particles in the nucleus, the valence electrons, all the electrons would be held more or held tighter. So ZF or ZF increases as you go across the period. So let me see if I can pull this little picture up. So you don't need to copy all of this stuff, but this is what I was talking about on the first one. We talk about shielding. Nucleus is positive. All these electrons are negative, so opposites attract. But as I increase my energy level, so that's energy level 1, energy level 2, energy level 3. So now these valence electrons, let's say that they're in energy level 4. They're not going to be held as tightly by this nucleus because all these other energy levels with their electrons are kind of shielding it or blocking it. It's getting in the way. So as you add more energy levels, the electrons get farther from the nucleus and the shielding increase. And both of those mean that they're not going to be held as tightly. All right. Everybody figure out where I'm at. I swear I'm having a Monday. Not that. Put it all back up here. There we go. I found it finally. Yay. Took me long enough. Okay, so let's look at those trends as we move down here. All right, so the first one that we're going to look at the bottom of your page is the atomic size, or the radius. Really, it's the radius. So we draw atoms like they're perfectly round, but that's not really true. It's kind of hard to get an exact size of it. So the way that we measure an atom is half the distance between the nuclei of identical atoms that would be joined as a molecule. So like if I had an atom and an atom, we're measuring from the center of one to the center of another. That's how we're getting that distance. The very smallest atom on the periodic table is helium, and the very largest is francium. And right here where it says trend, we're going to use arrows to represent the trend. So if I let these arrows represent which way it's increasing, atomic size increases backwards across the period, and it increases as you move down a group. So the reason it increases as you move down a group is because you're increasing your energy levels. So I'm adding more size just from that and increasing the shielding. And the reason that it increases as I go backwards is because you see a decrease in that ZEF, or effective nuclear charge, within a period. If I go backwards, then I'm decreasing the number of protons that are in the nucleus. So the electrons are going to be held less, and then they're allowed to spread out and get larger. So the reason that these become kind of important as you do your practice, if you have trouble with the arrows, visualizing that, sometimes if you know which one's the smallest and which one the largest, then you can just compare everything to that. So if I gave you a list of 5 different atoms and I asked you which one was the smallest, you would want to choose the one that was closest to helium. So it's just kind of a different way to kind of attack the different trends if one way isn't working for you. All righty, on the next one we have is ionization energy. And it's the measure of the ease with which an electron can be removed. So the higher the ionization energy is, the harder it is to remove the electron. And the first ionization energy is always going to be less than the second ionization energy. And even then it would keep on. If I had third, then third would take the most. So like magnesium, which is group 2, and it wants to lose 2 electrons, it's going to take a certain amount of energy to get the first one, and then even more energy to get the second one, because that second electron would be held tighter to the nucleus. So helium has the highest ionization energy and francium has the lowest. And they happen to be the 2 extremes for several different trends. And if we looked at the trend with arrows, ionization energy increases as I go across and as I go up a group. So it's going to take more energy to try to remove electron from a non-metal than it does from a metal. The next one that we're looking at is the size of ions, whether they're going to be positive ions or negative ions. So the smallest is the hydrogen cation, H+. As smallest is just energy level 1, and then it's lost its 1 electron. So that's going to be your smallest one. And then your largest one would be your iodide anion. That's your I-. Iodide is period number 6, so 6 energy levels out, and then on top of that, it gains an electron. So my trend on here is going to be increasing toward my nonmetals, and that's because they form anions. So they gain electrons, so they're gaining something. And then also when they gain the electron, it increases the electron repulsion. And then if we're looking at my metals, it's going to increase down because I'm adding energy levels. So cations are your positive ions, and they are always smaller than their parent ion. You can think of it that they're losing a particle, that makes them smaller, but now they have less electrons, same number of protons, so those protons will hold those electrons tighter. So metals have a low ionization energy because they lose electrons easily. Anions, on the other hand, which are your negative ions, are larger than their parent ions. They're larger because they're going to gain an electron and increase electron to electron repulsion. So the electrons are all in the electron cloud, which isn't very large. They all have a negative charge, so they're repelling each other already. Now I throw another electron in there, it's going to repel even more. So if it's repelling, it's pushing away from each other, and that's going to cause that ion to get larger. So nonmetals have high ionization energies. And they're larger than their original parent. All right, move this one up a little bit. All right, so next one that I have is going to be my electronegativity. It's the tendency of an atom to attract electrons to itself when it's chemically combined to another element. So that means when it's part of a compound. So the highest electronegativity for an element is fluorine. And it has a value of 4. Electronegativities are actually given numbers, and the very highest number anything could get would be 4, and that's from fluorine. And then francium is going to be your lowest. So that trend is going to increase electronegativity, ability to pull an electron itself. It's going to increase as I go across the period, and it's going to increase as I go up a group because less energy levels. So that positive nucleus would be felt more. All right, next one is electron affinity. It's the energy change that now accompanies the addition of an electron. And high electron affinity means an electron is more easily added. So my very highest is fluorine. And my very lowest is francium. Francium does not want an electron, so it has a low electron affinity value. So electron affinity increases also as you move across the period and then as you go up a group. And then the last one is metallic character versus non-metallic character. When you talk about metallic character, it relates to the ability to lose an electron. So metals, which make up most of our periodic table, they're going to have a higher metallic character than our nonmetals. Our nonmetals don't want to lose an electron, they want to gain it. So most of the elements are metals. The trend is less metallic as you go to the right of the table. So it's just kind of a pretty large trend, not really so much within a group or period. Because my metals are over here, as I'm start moving toward the non-metal, then that metallic character starts decreasing. All right, on the last page is just my periodic table with all of the different trends together, except for electronegativity, which we can add. All right. So if you want to add electronegativity to it, electronegativity is going to increase as I move from my metals to my non-metals, and then it's also going to increase as I move up a group. All right, so this is kind of some typical questions that you might be asked about trends. So it says, which element has the largest atomic size? So if I kind of just put these elements in, this is not just a perfect periodic table, but I can estimate them. I have lithium, sodium, and there is beryllium. So if I was given those three, which of those three would have the largest atomic mass? Not atomic mass, atomic radius. Sodium, exactly. Because if I look, my trend is it increases as I go down. So that means that sodium is going to be in the largest energy level. The trend is you increase as you go down, and then for atomic radius, it also increases as you move backwards across a period. So out of these, beryllium would be my smallest. It would get down to lithium and beryllium, but beryllium has a few more extra proton in its nucleus, so that's going to make it a little bit smaller. We also said that we had our two, on that particular one, if we would have looked at, since we were looking at what are we doing, the largest or the smallest? The largest, we said the largest of all would be francium. So if you looked at those three and you saw which one was closest to francium, you would come up with sodium again. All right, the next one, which element has the lowest ionization energy? Let's see, that's right. That's exactly right. All right, why don't y'all try those next 3 or 4? I think there's 4 of them. Try your next 4, see what you come out with. All right. So which element would have the lowest electronegativity? Si, let's see, let's go back and look at that one because I have nitrogen. Let me write those on there. Let's see. So we had this one, we'll say carbon was about here, nitrogen, oxygen, right? And then I have Si, S, and Cl about like that. So which one were we comparing on that one? Carbon, nitrogen, and Si. And my, where's my fluorine would be about right here. So carbon is the one that's easiest to get rid of, right? And then if I get between nitrogen and Si, electronegativity increases as I move this way. And it also increases as I move up. So it would actually have to be nitrogen. Nitrogen is closer to fluorine. It's also up an extra an energy level. So on that particular one, you would have to have nitrogen. Oh, I don't want my highest. I want my lowest, don't I? Yes. Then I would want my Si. Thank you. I could read on this particular day. All right. So which atom would be the largest? Sodium ion or sodium atom? The sodium atom would be the largest. And then between the sulfur ion or the sulfur atom. And remember, if it's the sulfur ion, has it gained or lost electrons? Because it's a nonmetal. It's gained electrons, right? So that negative is always going to be larger than the original atom. So the sodium atom would be the largest, and then the sulfur ion out of those two would be the largest. Which one has the highest ionization energy? Oxygen. And then which element has the highest electronegativity? Fluorine, what I was trying to do on the last one. All right, so what time do we get out of here? Pretty quick. Okay, so the practice, like I said, the one with the answers is the practice. The other one hopefully will make a little bit more sense to you. It's just a way of kind of coming up with like a little cheat sheet that you kind of just do the trends over the main element. It's not going to have every transition metal in it. And I will be here this afternoon if you need to make anything up. Nice Monday.